Hi, I'm Brasoveanu, and I will talk about reinforcement learning for production-based cognitive models. This is joint work with Dotlačil. The overarching goal for this research project is to explore how complex production-based cognitive models of linguistic skills can be acquired. Cognitive model learnability is largely understudied for linguistics, since we just started using such models more widely. Furthermore, the learnability problem is more difficult for models of linguistic skills versus other high-level cognitive processes because committing to theoretically grounded models requires us to hand-code complex systems of representations and rules. So, the question arises, can such complex rule systems be learned from the data? The learnability problem can be divided into two parts: rule acquisition, which is forming complex rules out of simpler ones, and rule ordering, which is deciding which rule to fire when. Actar's solutions to these two subproblems are production compilation for rule acquisition and rule utility estimation for rule ordering. Neither has been systematically applied to models of linguistic skills, with few exceptions in the previous literature. Our contribution is to focus on the easier problem 2, rule ordering, and show how reinforcement learning methods can be leveraged to formalize and partially solve it. This is the roadmap for the talk. We're just done with the introduction, and I will now move on to introducing the kind of task that we're going to be modeling. Parsing is too complex. The range of issues that emerge when systematically integrating Actar and RL are best showcased with a simpler example. We will choose a basic learning algorithm, tabular Q-learning, and we will focus on a very simple task, lexical decision, which is a task in which participants see a string of letters on a screen. If they think the string is a word, they press one key, J, in our setup. If they think the string is not a word, they press a different key, F, in our setup. After pressing the key, the next stimulus is presented. Our specific goal is to investigate the extent to which the Q-learning agent can be used to learn goal condition rules in an Actar-based cognitive model of LD tasks. The model for LD task is simple, as we mentioned, so it is a good starting point, but it is a component of more complex syntactic and semantic parsing models, so can be scaled up. We will model 3 lexical decision tasks of increasing length, hence difficulty. A one-stimulus task, where the word elephant is displayed on the virtual screen for the Actar model. A 2-stimuli task, in which the word elephant is displayed, then a non-word. And finally, a 4-stimuli task, in which the word elephant is displayed, then a non-word, then the word dog, and then another non-word. The model components will be split between declarative memory, which will store the lexical knowledge of an English speaker, and procedural memory, which stores production rules that enable the model to carry out the lexical decision task. We need 4 production rules to model lexical decision tasks. The first rule, retrieving, reads a string of letters on the virtual screen of the Actar model, then places a retrieval request to declarative memory for a word with that form. This request can complete successfully or unsuccessfully, depending on whether the string of letters is a word or a non-word. If the string of letters is a word, so the declarative memory retrieval request completes successfully, then rule 2 fires, and we press the J key. If the retrieval request completes unsuccessfully, because the string of letters is a non-word, then rule 3 fires, and we press the F key. Rule 4, finished, closes the simulated lexical decision task as soon as the string of letters finished is displayed on the virtual screen. Goal state preconditions are stricken out in these rules because the Q-learning agent is supposed to learn them. However, if we work with rules that have fully specified goal state preconditions, and we assume that the initial goal state of the Actar model is retrieving, this is how a simulated LD task will proceed. The word elephant appears on the virtual screen of the model. It is automatically stored in the value slot of the visual buffer, at which point the preconditions of rule 1 are satisfied, so the rule fires, and as a consequence, we attempt to retrieve a word with the form elephant from declarative memory. And when the word is successfully retrieved, rule 2 fires and the J key is pressed. Then, depending on which task we are looking at, the following sequences of actions happen. In the one-stimulus task, the text finished is displayed on the virtual screen, in which case rule 4 fires and ends the task. In the 2-stimuli task, the non-word is displayed, then rule 1 fires again, placing a declarative memory request for a word with that form. The retrieval attempt fails, so rule 3 fires and the F key is pressed. Then the text finished is displayed and rule 4 fires to end the task. In the 4 stimuli task, after the word elephant, the first known word is displayed, rule 1 fires, then rule 3 fires and the F key is pressed, then the string dog is displayed, in which case rule 1 fires, then rule 2 fires and the J key is pressed. Then the second known word is displayed, rule 1 fires, placing a declarative memory request for a word with that form. That request fails, then rule 3 fires and the F key is pressed. Finally, the text finished is displayed and rule 4 fires to end the 4 stimuli task. The sequences of rule firings for the 3 LD tasks are as follows. For the 1 stimulus task, the rules are 1, 2, and 4. For the 2 stimuli task, rules are 1, 2, 1, 3, and 4. And for the 4 stimuli task, the rules are 1, 2, 1, 3, 1, 2, 1, 3, and 4. We let the Q-learning agent learn to successfully carry out these LD tasks. The agent gets a reward of 1 if it reaches the final goal state done, a small negative reward of minus 0.15 for any intermediate rule firing, and this small negative penalty encourages the agent to finish the task as soon as possible. Finally, the agent gets a 0 reward, so no penalty, if it chooses to wait and fire no rule. This encourages the agent to wait if that is the optimal course of action, which it is when waiting for retrieval requests from declarative memory to complete, for example. The agent will learn by trial and error how to properly order the rules and complete the LD tasks as efficiently as possible. This is no small feat. The actual number of steps, so decision points, when the agent needs to select an action, is larger than the high-level sequences of rule firings discussed above. For the 1 stimulus task, we actually have 12 steps where the agent needs to decide whether to wait or to fire a specific rule. When the agent does not complete the task perfectly, it takes much more than 12 steps. For the 2 stimuli task, the agent needs 18 steps if the task is completed perfectly, and for the 4 stimuli task, the agent needs 34 steps if the task is to be completed perfectly. There are many more steps per task than the high-level rule sequences we just discussed, because lexical decision simulations involve the visual and motor modules, in addition to the declarative memory module, and visual and motor actions, just as retrievals from declarative memory, take time, and the agent needs to make decisions while waiting for them to complete. The higher the number of steps, the harder the task is to learn, so that means that learning is faster and less noisy for shorter tasks with fewer stimuli. But the Q-learning agent learns even the most complex 4 stimuli task fairly well. It just also learns a lot of noise in the process. Turning now to formulating the production rule ordering problem as a reinforcement learning problem, we will introduce Markov decision processes, which are deterministic or stochastic models of decision-making sequences, which are the basis of reinforcement learning approaches to learning. In an MDP, an agent interacts with its environment and needs to make decisions at discrete time steps, t, 1, 2, and so on through n, which is the final time step. At every time step t, the current state, s sub t, provides all the information relevant for the current action selection. This is the Markov property. The environment passes to the agent this state and the reward signal r sub t. The agent observes the state and the reward, and then takes an action a, which is passed from the agent back to the environment, and then the cycle continues at time step t+1. The agent's policy is a complete specification of what action to take at any time step. Given the Markov property, the policy pi is a mapping from the state space S to the action space A. The agent goal is to maximize some form of cumulative reward over an episode, where an episode is defined as a complete, usually multi-step interaction between the agent and its environment. In our case, an episode would be a full simulation of a 1, 2, or 4 stimuli task. Learning means that the agent updates its policy pi to maximize the per episode cumulative reward. The discounted return g is the sum of the current reward r sub t+1 and discounted future rewards until the final time step n. The discount factor gamma, between 0 and 1, determines the present value of future rewards. The state action value function q sub pi, or simply the action value function q, provides the expected discounted return when starting in state S, performing action A, and then following the policy pi until the end of the episode. We can improve our estimate of the Q function based on interactions between the agent and the environment. And an optimal policy, which is a policy that maximizes return, is to choose a maximum value action in any given state. We represent the Q function in tabular Q-learning as a lookup table storing the estimated values of all possible state action pairs. The Q table is initialized to an arbitrary fixed value, usually 0. And at each time step, we update the entry for the state and action at that time step based on the information the agent gets from the environment at the next step, namely the reward R sub t plus 1 and the new state S sub t plus 1. In our actor model of lexical decision tasks, the agent is the Q value table that guides rule selection at every cognitive step. The environment is the cognitive state of the actor model, or mind. The states that the environment passes to the agent consist of the current goal buffer, the current retrieval buffer, the value in the visual what buffer, if any, and the state of the manual buffer. The action space consists of the 4 rules retrieving, lexeme retrieved, no lexeme found, and finished, and the special action none, which the agent selects when it prefers to wait for a new state. The reward structure, which we already discussed, encourages the agent to finish the task as soon as possible by selecting the fewest rules. We get a positive reward when the LD task is completed. We get a small negative reward of minus 0.15 for every rule the agent selects other than none. There is no penalty for selecting the special action none of waiting. Furthermore, at every time step, a negative reward equal to the amount of time that has elapsed between the immediately preceding step and the current step is passed to the agent. And this negative temporal reward discourages the agent from just repeatedly selecting the special action none, for example, which will quickly time out the LD task in a very small number of rules and fast forward the agent to the maximum waiting time the actor environment allows for, which we set to 2 seconds per stimulus in LD tasks. Turning to simulation and results now, we used an epsilon greedy policy for all simulations, with epsilon annealed from 1 to a minimum value of 0.01. For the one stimulus task, we simulate 15,000 episodes, and we see that the agent learns to complete the task perfectly in about 12 steps after about 5,000 episodes. To see what the agent learned, we look at the final Q table, and within that Q table, we only look at the states for which at least one action has a non-zero value. There is a total of 8 such states. For each state, we identify the action rule with the highest value, and we see that there are 3 states in which the agent fires no rule. That's when the agent waits for the text to be auto-detected from the virtual screen and stored in the visual buffer, or when the agent waits for the retrieval process to complete. There are 3 states where the maximum value action is finished, and again, this makes sense. In all of them, the visual value is the text finished. The final 2 state action pairs are as follows. In one of them, the agent has just stored the string displayed on the virtual screen, which is elephant, and correctly starts a retrieval process by selecting the retrieving rule. In the second state action pair, the retrieval process has been successfully completed, so the retrieval buffer actually contains a word with the form elephant, and the agent correctly selects the lexeme retrieved rule, rule number 2, and presses the J key. Thus, it seems that there is no need to hand code goal states and rule preconditions. The Q-learning agent manages to learn by trial and error when to fire which rule and when to wait. For the 2 stimuli task, we also run 15,000 episodes, which means 15,000 lexical decision tasks with 2 stimuli, elephant and a non-word. The agent learns to complete the task about perfectly, so in about 18 steps, after about 9,000 episodes. In the final Q table, there are 13 states with at least one non-zero value action. 4 states are states in which the agent does nothing, and it makes complete sense. It's when the agent waits for the retrieval process to complete, either for the word elephant or for the non-word, and when the agent waits for the visual value displayed on the virtual screen, so the word elephant or the non-word, to be stored in the visual buffer. The 4 stimuli task requires about 25,000 episodes for learning to happen, and the task is completed reliably, which means in less than 40 steps, after about 22,000 episodes. The final Q table has 24 states with at least one non-zero value action. 18 are exactly what we would expect, and they make sense. 6, however, reflect the noise in the trial and error learning process. To conclude, we have shown that the learnability problem for production-based cognitive models can be systematically formulated and computationally addressed as a reinforcement learning problem. But this is merely a first inroad into a rich nexus of issues. More details are provided in the paper, which is available on the website. Thank you.